Good day and welcome back to part one of our discussion on the limit of a function. The goal of this video will be to remind us of what we talked about in the previous section and use that to transition into what we'll think of as the intuitive definition of a limit and then explore an associated example. So recall from our previous section, we started off by investigating how we could find the slope of a tangent line. And what we saw is that the slope of the tangent line is a limit, whatever that means, of the slopes of secant lines. And the specific example that we investigated was the square root function at x equals 1. So if we were to draw this tangent line at x equals 1, the problem with writing down its equation is we need to determine its slope, and we only know one point on that tangent line. 1, 1. So in order to come up with the slope of the tangent line, we said, how about we consider another point on this curve? Let's call it Q and have it be x square root x. And if we draw the line going through both of these points on the curve, pretend it really does intersect at just those 2 points, we would call this a secant line. And note, because we have 2 points on the secant line, we can calculate its slope with no problem. And we can use that to determine the slope of the tangent line. The idea is going to be that as we let this x value approach 1, if we draw in a few more of those secant lines, what we would see is that they start to almost kind of rotate around, and the blue line will more closely resemble and eventually be indistinguishable from that tangent line. So what we saw is that the desired slope we are looking for is the limit as x approaches 1 of what we called MPQ, the slope of the secant line. And in terms of a formula in this case, that would be rise over run. And what we would like to do in this section and the next as well is really investigate what is it that we mean by the limit of a function. So let's start off with just what is the intuitive definition? How can we think of as a limit? So if we see these symbols, the limit as x approaches a of f of x equals L, we want an idea of what this means. And what this is indicating for us is if we have an input close to a, that's where our x values are, those associated function outputs f of x will be close to L. So that means very intuitively, for x close to a, f of x is close to L. And what we're going to have to make sense of is what does it mean, for two quantities to be close? That's a relatively vague or nebulous term. So the best thing we could possibly do is maybe to investigate an example. So for the function f equals x cubed minus 1 over x minus 1, let's just fill in this table of values to see if we can figure out what happens when x is close to 1. And the first thing I'm going to do is go ahead and note we cannot plug 1 into this function. This function is undefined. There is no output at 1. But don't worry, because we never sit above here that x has to be equal to a, just that it needs to be close to a. And if you were to go ahead and use a calculator, say, and figure out some of these function values. If x is 0.75, we would get 2.313. At 0.9, we get 2.716, and then 2.970. And a common question I find that I'm asked in these initial sections is, how many decimal places of accuracy do we need to use? And the answer is, it depends. You need enough so that it's reasonable for the given problem. And to be 100% honest, we're going to use a calculator to fill in tables such as this one more in the first 2 sections of the semester than we probably will for the next 20 sections. So enjoy it while it well, less, I guess. Now, filling in from the right, if you substitute in x equals 1.1, we get 3.310. 1.01, we get 3.030, and then 3.003. And going back to this intuitive definition of a limit, we said that for x close to a, what are those function outputs going to be close to? And if we notice for inputs close to 1, what do those function outputs look like they're getting close to? It looks as though from the left-hand side they're approaching 3, and from the right-hand side they're approaching 3. So from this table of values, I can't say anything with 100% certainty, but what I can do is make a very educated guess. It appears to me that the limit as x approaches 1 of x cubed minus 1 over x minus 1 is equal to 3. For inputs close to 1, these function outputs appear to be close to 3. And let me go ahead and get a little bit of intuition as to why this might be true. So let's just make a few observations. First, we'll work with the function analytically, or just use some algebra, and then we'll sketch a corresponding picture. So f of x equals x cubed minus 1 over x minus 1. And you might observe x minus 1 is a factor of x cubed minus 1, which means we should be able to simplify this expression. So you can rewrite the numerator as x minus 1 times x squared plus x plus 1, which means the x minus 1's cancel with each other. So what we can observe from this is as long as x is not equal to 1, because note, when x is equal to 1, that function is undefined. There is no associated output. But if we stay away from that, what we have is that f of x is x squared plus x plus 1. And you might observe, for inputs close to 1, our outputs are going to be close to 3. And let's actually now take this work and use it to sketch a graph of our function. So roughly speaking, if you wanted to graph the function f, we can just graph x squared plus x plus 1, and then leave an opening where the function is undefined at 1. And if you were to graph x squared plus x plus 1, what we can observe is that it has a y-intercept of 1, i.e. when x is 0, the output is 1. And roughly speaking, it's going to look something like this. And note that really should be a parabola. So as you'll hear me say multiple times throughout the semester, your pictures do not need to be perfect. Just get kind of those relevant details across. And what we want to observe from this graph is the intuitive definition of the limit. For inputs close to, in our case, 1, the function output should be close to 3. So let's see here. If I pick a value close to 1, but maybe not at 1, so let's just go ahead and call this x1. If you trace up to the curve, what you'll find is the function output is going to be close to 3. And similarly, if we pick some function value close to 1 on the right, maybe call it x2, that associated function output is also going to be close to 3. And what we've done here is introduced the intuitive definition of a limit, and we've investigated it with one specific example. In our next video, we will explore a more precise definition or mathematical definition of the limit and explore the graphical interpretation, how we can investigate this in terms of the graph of a function. So stay tuned and take care.